This is your presenter Asloob Mudassar, and I am presenting slide number 81 of the course on laser physics. Question is, discuss the physics of a Gaussian beam in free space propagation under Paraxial approximation. Discuss how the beam spot size and radius of curvature of the beam vary with propagation distance. How can the beam with higher order modes be constructed? Note that most lasers operate with nearly Gaussian profiles or with their higher order modes. The answer is Fresnel Kirchhoff integral in the Fresnel approximation can be used to discuss the properties of the Gaussian beams under Paraxial approximations. Let us assume a general optical system lying between two parallel planes as shown in figure 80.2. That is, this figure is from the previous slide, but in the appendix I have added this figure. So let's see that figure. So this is the figure, which is 80.2, and you see that in this figure you have two parallel planes. One is located at z is equal to z1, the other is located at a general distance z is equal to z. Both planes are parallel to each other and perpendicular to the z axis. The field at the plane z1 is u of x1 y1 z1, which is assumed to be known, and the field at the point at any plane z is equal to z is u of x y z, which is to be determined. And the both planes shown in dotted contain a general optical system. So this is the system that has been referred over here. Let's assume a general optical system lying between two parallel planes as shown in figure 80.2. For simplification, by the integral approach, we assume that no limiting aperture is located at the z is equal to z1 input plane, and we can use the limits from minus infinity to plus infinity for both the variables x1 and y1. Let us assume that the field at the input planes to be defined as u of x1 y1 z1 is proportional to e to the power minus iota k, and then we have x1 square plus y1 square divided by 2q1. So this is the field that we are assuming, or that the field we have defined at the input plane, that is at this plane. And we are assuming that these planes located at z is equal to z1 and at z is equal to z are of infinite extent, and that there are no limiting aperture at the input plane or at the output plane. What is Q1? So Q1 will be, I shall address about Q1, details about Q1 later, maybe in the next page. Solving the integral in equation number 80.9. So what is this equation? So let me show this equation also, 80.9. That is from the previous slide, but I have appended it over here. So this is equation number 80.9. You see that this equation gives you the field at the output plane, that is the field u as a function of x, y, z, that is equal to iota over b times lambda. The double integral over the surface area is equal to u of x1 y1 z1, which is the input field, which is the field at the input plane, and then multiplied by this whole exponential factor e to the power minus iota k, and then we have the curly brackets containing a of x1 square plus y1 square, and then plus d multiplied by x square plus y square minus 2x1 x minus 2 y1 y over 2b. So this is a part of the exponent, and then we have integration with respect to dx1 and dy1. So this is the integral that I am referring over here. Solving the integral in equation number 80.9 gives the field at the output plane. So this is what I have now written the field in another form, that is u of x, y, z is equal to 1 over a plus b over q1 multiplied by e to the power iota k, and then multiplied by x square plus y square over 2q. So what is q? Q is related with q1, because I have defined q1 over here but not explained. So here I am giving you the relationship that q in equation number 2 is related to the q1 in equation number 1 through the relationship that q is equal to a times q1 plus b divided by c times q1 plus capital D. The field given by equation number 2 is referred to as the ABCD law of Gaussian beam propagation. It relates the complex radius of curvature q. So here notice that q is actually a complex radius of curvature of a spherical Gaussian beam at a distance z to the same quantity at a distance z1. So you see that here q, what is q? Q is actually the complex radius of curvature at the plane z is equal to z, and where q1 is a complex radius of curvature at the spherical beam at a plane z is equal to z1. So let me refer to you over here in the figure that we have q is the field, is the radius of curvature of the spherical field at the output plane, that is at z is equal to z plane, and q1 is actually the radius of curvature of the spherical wave at the input plane, that is at z is equal to z plane. So now q1 and q2 are clear. But you know that q1 and q2 have been referred to as the complex radius of curvature, and these will be explained over here, and we have defined q over here. So 1 over q as a function of z is equal to 1 over capital R as a function of z minus iota times lambda over pi into w square as a function of z. So here we have three variables, q, capital R and w square. So these three quantities are a function of z, and we have linked them together through the relationship where R is the real part of the radius of curvature. From equation number 80.3, we have the following equation, that is the field, that is E prime at xyz is equal to u of xyz multiplied by e to the power minus kz, where u of xyz is actually the spatial part of the field at the plane z, and e to the power iota kz is the phase vector. That is, you see that depending upon the value of z, so it covers actually the phase relation, it covers the phase variation from the z is equal to z1 plane to the final plane which is equal to which is the z is equal to z plane. So we have E prime as a function of xyz is related with the spatial part of the disturbance, which is u of xyz multiplied by the phase factor e to the power minus iota kz. So thus we can write that E of xyz is proportional to the e to the power minus iota k, and the parenthesis contains z plus x square plus y square over 2q. So you see that this is the same field as given above, but now we have represented this field in a very general form in terms of the complex radius of curvature q. What are x and y? X and y are, you know, that are the coordinates at the input plane or at the output plane, and you know that xy is the plane which is perpendicular to the z axis in the figure that we have been discussing and given in the appendix. So this is the more general form. This gives you the field at the location z, and then we have this function which is multiplied over here. So we have z, you see that z is also minus iota kz is also present in the above equation. So we have e to the power minus iota kz, and then we have an additional factor that we have multiplied over here, which is e to the power minus iota k into x square plus y square over 2q. Now we have written the field, that is the field is proportional to this quantity. We shall be explaining this field further. Substituting q of z from equation number 81.4 we obtain, that is from equation number 4, we can take the value of q of z and we can substitute over here in equation number 5. then we can write down that we obtained this relationship, that E prime as a function of x, y, z is proportional to the e to the power minus x square plus y square over w square multiplied by e to the power minus iota k, and then within the parentheses we have z plus x square plus y square over 2r. So you see that here we had 2q, now we have instead 2r over here, where r is the radius of curvature of the wavefront, probably the spherical wavefront, and we have this vector e to the power minus x square plus y square over w square. This is actually the function that gives the shape of a, that is the Gaussian function, and gives you the shape of a Gaussian profile. So we have this, you see that field E prime of x, y, z, which is proportional to the two terms, and as given in equation number 6. In terms of the radial beam coordinate, that is, we can introduce r instead of x square plus y square, and that will be r is equal to square root of x square plus y square. So we can rewrite equation number 6 in the following form, that is E is as a function of r and z is proportional to e to the power minus r square over w square, and then e to the power minus iota k over, within parentheses we have z plus r square over 2 capital R. So here we have expressed the same field as represented in equation number 6. Now in the variable, in terms of the variable r, where r is equal to the square root of x square plus y square, we have the same equation number as given in equation number as given in 7. So 6 and 7 are identical, only just a matter of change of variables. Now you see that the plot of the amplitude term, here you see that in equation number 7, or in the proportionality of the equation number 7, you can see that e to the power minus r square over omega square is actually an amplitude term. So the plot of the amplitude term, that is e to the power minus r square over w square, versus the, this is not omega square, this is actually w square. I shall be explaining w square further in detail in the next few slides. So e to the power minus r square over w square versus the normalized distance, which is r over w, from the center of the beam is shown in equation number, is shown in figure number 81.1. The curve has a Gaussian profile with the beam radius indicated at 1 over e point. So let me explain the figure. So you see that the horizontal axis, we are plotting r over w along the horizontal axis, and along the vertical axis we are plotting the amplitude of the wave contribution at the output plane, which is e to the power minus r square over w square. And of course, since e to the power minus r over w square is a Gaussian function, so you see that we have a Gaussian profile. Now if you set r is equal to w, for example, you will get e to the power minus 1, that is 1 over e. And you see that we have a dotted line shown at a position of 1 over e. So 1 over e has been shown over here, and 1 over e is the point. You see that we get 2 points on the curve. I have shown only 1 point at just above the value of r or w equal to 1. But at r is equal to w is equal to minus 1, you will get another point which is also 1 over e point. So you shall get 2 1 over e points. So the 1 over e points will determine the width of the laser spot, or the width of this Gaussian function. And since this Gaussian function is actually representing a laser in our case, a laser beam in our case, so we have 1 over e points which give you the width of the laser beam in terms of amplitude, because we are plotting the amplitude, not the intensity. And you see that this 1 over e points are obtained when r is set equal to w. And you see that this is the historical way of obtaining the 1 over e points, and or in other words, obtaining the spot size in terms of the amplitude. So let me read the caption. Plot of amplitude term from equation number 7 versus the normalized distance from the center of the beam. So this O, this is 0 is at the center of the beam, where the intensity or where the amplitude is maximum. But as you go away from the center of the beam, you will see that the amplitude of the beam will fall on both sides. Then you see that we can measure the laser spot in terms of the amplitude at 1 over e points. So there are two 1 over e points starting from -1 to +1, -1 to +1, the value of r over w. So it means that for r over w, that could be r is equal to -w to r is equal to +w. So this is the actually the width of the laser spot in terms of the amplitude. For r is equal to w, the amplitude drops to 1 over e of its maximum value. It gives the practical value of the beam spot. So you see that here you have noticed that r is equal to, if you set r is equal to w, you get 1 over e points, and 1 over e points will give you the width of the beam on this curve. So that width of the beam is actually a practical way of finding the beam spot or finding the diameter of the beam spot. The beam intensity is defined as, you know that intensity is linked is proportional to the absolute square of e prime, where e prime has been defined in equation number 7. So if you take the absolute value of this quantity, you will see that this factor, which is e to the power minus iota k times some within the parentheses, this factor will eliminated by taking the absolute value. So we have intensity which is proportional to now e to the power minus 2 times of x square plus y square over w square, represented in x and y coordinates. Or you can also write it as -2 times r square over w square if you want to use the representation in terms of the r variable. So our intensity is proportional to now this quantity. Or we can write this proportionality sign into the equality sign by introducing Im. So I is equal to Im into e to the power -2 times of x square plus y square over w square, or -2 times r square over w square, as shown in equation number 8. The practical beam radius is considered where the intensity falls to 1 over e of its maximum value. To obtain that value of radius, we set I is equal to Im over e, or equivalently I is equal to Im into e to the power -1. So if you set the value of I on the left hand side is equal to Im into e to the power -1 and solve the rest of the equation, you will get this equation, which is 2 into within the parenthesis we have x square plus y square over w square is equal to 2 times of r square over w square is equal to r square over, so this 2 can be combined with w in the form that w over w divided by square or square root of 2, the whole square of this quantity. So r square divided by the square of w over square root of 2, and that is equal to 1. Because if you substitute Im is equal to -1 over here on the left hand side, Im will be cancelled and you have on the left hand side e to the power -1. So you can compare the two powers of the e value from the left hand side and from the right hand side, and you will get that -2 into x square plus y square over w square will be equal to -1. And -2 minus with 2 will cancel with -1 with the negative sign with 1 on the left hand side, and then you will have only 1 left with there. So that's why I have set this one. You see that solving this equation you will get r is equal to w over square root of 2. So for this value of as far as the intensity is concerned, the 1 over e points are obtained when you set the value of r is equal to w over square root of 2. But you know that when you talk about the amplitude, 1 over e points are obtained when you set r is equal to w. But for the case of intensity, you need to set r is equal to w over square root of 2 if you want to obtain the 1 over e points. So at this value of r, from the beam center radially outward, that is along any direction outside from the radius, the intensity decreases to 1 over e of its maximum value. Thus the equation number 9 gives the practical radius of the Gaussian beam. Of the Gaussian beam in the intensity form. And you know that intensity is a quantity that is a physically measurable quantity, and in practical sense we always talk about the Gaussian intensity beam. And you know that the diameter of that Gaussian intensity beam can be obtained from this value of r. So when you set this value of r, you will find out 1 over e points, and between the two 1 over e points on the intensity laser spot, you will get the diameter of the laser beam or the laser spot. Now let's consider the phase factor e to the power minus iota k into z plus r square over 2r in equation number 7, and let's try to interpret the phase term. That is, now we are going to interpret the term, the exponent, the phase term in equation number 7, which is e to the power minus iota k. Within parentheses we have z plus r square over 2r. So let's try to explain this term. So you see that term can be expressed as z plus x square over y square over 2r can be represented as z into, within parentheses we have 1 plus x square plus y square over 2rz. So if you take z common from these two terms, you have z outside the parentheses, and then we have the term 1 plus x square plus y square over 2 capital R into z. So you see that now this can be written as z minus 0, and within the parentheses we have 1 plus x minus 0 whole square plus y minus 0 whole square, and in the denominator we have 2 times of r multiplied by, within parentheses we have z minus 0. So it means that we have 0 at x minus 0, y minus 0, z minus 0. It means that the wave is originating from the point 0, 0, 0. That is, the wave is originating from the 3-dimensional origin of the coordinate system, which is 0, 0, 0. Then if you set r goes to z, so if you set the value of r goes to z, so we can write the term as follow. So we are writing the above equation in the following form with r equal to z. So we have z square over here in the middle term, you can notice, and also we have r represented by z square because we have taken z common. So we have 2rz, and r is replaced by z, so we have 2z square. So you can see, notice 2z square over here. But you know that this whole term the term in the parenthesis can also be written as 1 plus x square plus y square over z square, and taken the power of this whole parenthesis is taken to be 1 over half, which means that if you expand this one as we have shown on the right hand side of that one, you will have the expansion. In the expansion you have 1 plus x square plus y square over 2z square plus for the higher order terms. So I am not showing the higher order terms because the first two terms are enough under the condition that z square is much greater than x square plus y square. That is, we are measuring the field at a value of z which is much greater than compared with the dimensions x square plus y square. So that's why we have ignored the higher order terms. And you know that if you retain only 2 terms of this expansion, you will see that this becomes the same as the term on the left hand side of this expression. So now we can write the middle expression, because we have proved that the middle expression is the same as the expression on the left hand side of it, or the equal to the expression on the right hand side. So the middle expression is written over here. And you see that if you take the LCM of this one, you will have, and if you multiply z inside, that becomes z square, and then over here z square will be cancelled. So you have x square plus y square plus z square to the power 1/2. That is the square root of this whole quantity. And you know that this quantity is nothing but r, because r is equal to square root of x square plus y square plus z square. So you see that this term, which is e to the power minus iota k, and within parentheses you have z plus r square over 2r, is actually can be written as e to the power minus iota k into r. And you know that from this one the shape of the figure is clear. The shape of this factor is clear. Thus the phase factor in equation number 7. So let me show you again. equation number 7, that is this term, and this phase factor that we have addressed and we have manipulated it, and we have shown that this phase factor is nothing but equal to e to the power minus iota kr. So thus the phase factor in equation number 7 can be identified as the spherical wave under paraxial approximation. So you see that this is our spherical wave, e to the power minus iota kr. So you can also write it as e to the power minus iota k, and r can be written as r minus 0,00, because r is originating from the origin. So thus the phase factor in equation number 7 can be identified as a spherical wave under paraxial approximation originating from the point 0,0,0, and capital R as the radius of curvature of the spherical wave front of the Gaussian beam. So you can see that here capital R is actually the radius of the Gaussian beam of the spherical wave, and similarly this R is actually a spherical wave having radius R, or that is or you can say that this is a spherical wave written at the position R, at a position point R. In equation number 5, so let me show you equation number 5, this one. So in equation number 5, the Gaussian beam can be viewed as a spherical wave of complex radius of curvature Q, given by equation number 4. Let's set the phase factor as. So you see that we are writing the same factor as given in equation number 5 as k into, within parentheses we have z plus x square plus y square over 2r equal to k times z prime. In equation number 5 you see that it is q dependent, and you know that 1 over q has been defined in equation number 4. So if you substitute the value of q over here, you will get a factor. For example, in equation number 6 you will get a factor which is dependent upon the value of capital R. So actually this factor, which is z plus x square plus y square over 2r, can be written as, so I am talking about this factor appearing, this phase factor appearing in equation number 6. So this phase factor can be written as k into z plus x square plus y square over 2r, can be written as x into z prime, because the whole term in the parenthesis can be approximated as z prime, because here we have defined actually the terms within the parenthesis to be equal to z prime. That is the value of the phase term at a distance z prime. Then we can write, so if you solve this equation for the value of z in terms of z prime, you will get z is equal to z prime minus x square plus y square over 2 times capital R. That is the equiphase surfaces are paraboloid of revolution around the z axis. So you see that if you notice that if you have enough mathematical knowledge with you, you will notice that this represents equiphase surfaces. Equiphase surfaces are the paraboloids of revolution about the z-axis. So this represents paraboloid of revolution about the z-axis, and these will form the equiphase surfaces. For free space propagation along the z-axis without any limiting aperture on the path is given by equation number 2, with q defined in equation number 3. So let me show you equation number 2 and equation number 3. This is equation number 2 and this is equation number 3. So equation number 2 gives you the field at the output plane, and you see that you can notice that the phase factor in terms of q is present, and then q can be expressed as shown in equation number 3 in terms of the q1 parameter. And you know that q and q1 are actually the complex radii of curvature of the spherical Gaussian beam at the output plane and at the input plane respectively of the figure shown in the appendix. Okay, So you see that for free space propagation we need to set A is equal to 1, capital D is equal to 1, capital C is equal to 0, capital B is equal to Z, because the separation between the two planes in the figure shown in the appendix is Z. So capital B is equal to Z, and this gives you Q is equal to Q1 plus Z. And you know that Q is nothing but radius of curvature of the spherical wave. Okay. So for the free space propagation you need to set these values in equation number 2 and 3, and then you will get this relationship. Otherwise you see that the relationship is slightly complex in the general form, that is Q is equal to A into Q1 plus B over C into Q1 plus D. So for the free space propagation you see that A is equal to 1, capital D is equal to 1, capital B is equal to Z, and capital C is equal to 0. And under that condition you will get a very simple result for the free space propagation, that Q is related with Q1 plus Z as shown in equation number 10. The value of Q1 can be obtained assuming that R goes to infinity at Z is equal to 0. That is, the wave has a plane wave front at Z is equal to 0. This gives the equation, this from equation number 4 follows over here as shown in equation number 11, that 1 over Q1 is equal to minus iota times lambda over pi into W naught square. So let me show equation number 4, and we are setting R goes to infinity in equation number 4. So here equation number 4, if you set R goes to infinity, then you will get 1 over Q, 1. So this Q will be replaced by 1 over Q1, and then we have the rest of the quantities. So setting R is equal to infinity, when you set R is equal to infinity, what is the meaning? It means that the curvature of the spherical wave is very, very large, that is a plane wave. So setting R is equal to infinity actually means that you are considering a plane wave. A plane wave at Z is equal to 0. So R is equal to infinity at Z is equal to 0 means that you get this relationship. 1 over Q1 is equal to, you see that I have replaced in the equation 1 or Q1, because you see that if you set Z is equal to 0 in equation number 10, you will see that Q can be replaced by Q1. So setting R goes to infinity and setting Z is equal to 0 with the help of equation number 10, and from equation number 4 you will obtain 1 over Q1 is equal to minus iota times lambda over pi into W naught square, where W naught, you see that now here we are going to define W naught for the first time, where W naught is the beam spot size at the location Z is equal to 0. That is over here. So here we have Z is equal to Z1, and here we have Z. So Z is equal to 0 may exist somewhere, maybe within the optical system. If Z1 for example is negative, and if capital Z is positive, then Z is equal to 0 will exist within the general optical system. Okay, so you see that we have this relationship for the Q1 that we have obtained. What is W naught? W naught is the beam spot size at the location Z is equal to 0. So what is the size of a beam spot at the location Z is equal to 0? That is we are referring to as W naught. Thus equation number 10 takes the following form. So using the value of Q1 from equation number 11 and substituting over here in equation number 10, we get the value of Q, that Q is equal to iota times pi into W naught square over lambda plus Z. Substituting a Q from equation number 12 into equation number 4 and comparing the real and imaginary parts in the resulting equations give you. So this is the value of q that we have obtained from equation number 12. Now substituting this value of q into equation number 4, that is in this equation, and comparing the real and imaginary parts on both sides of this equation, we get two equations. One corresponding to the real part and the other corresponding to the imaginary part. So we have w square of z is equal to w naught square, and with the square bracket we have 1 plus square of lambda z over pi w naught square, and for we have r of z also, which is equal to z times within the square bracket we have 1 plus square of pi w naught square over lambda z. So you see that we have obtained these two results. You see that in as far as equation in equation number 13, you know that w naught is actually the beam spot size at the location z is equal to 0, and w of z is actually the beam spot size at the location z, and this is what the square of that quantity. So w of z can be obtained by taking the square root of both sides of this equation, and on the left hand side then we shall have w of z, and on the right hand side we shall have the square root of all this quantity. So you see that this expression, that is equation number 13, gives you to calculate the spot size of the laser beam at a distance z at any value of z in terms of its initial spot size w naught defined at the location z is equal to 0. Similarly, r of z, which is the curvature of the spherical wave front of the Gaussian beam propagating within the laser cavity, can also be obtained from this relation. And you know that when you set r goes to infinity, it means that at the location z is equal to 0 you have a plane wave front. But when the light will travel on either side of z is equal to 0, that is on the positive side or on the negative side, you have this value of r, which is given by r of z equal to as shown in equation number 14. So equation number 13 gives the spot size of the beam as a function of z, and equation number 14 gives you the radius of curvature of the beam as a function of z. Thus equation number 13 and 14 gives you the spot size of the beam and the radius of curvature of the beam as a function of z. Using q1 from equation number 11, that is q1 from this equation, and the Gaussian beam from equation number 2 in paraxial form in free space takes the following form. So let me show you equation number 2. This is equation number 2, and we are going to substitute the value of q1 from equation number 11, and after inserting the q1 from equation number 11 into equation number 2, we get the results that a field at the point x, y, z is equal to 1 over 1 minus iota times lambda z over pi omega w naught square, and then multiplied by the phase factor e to the power minus iota k multiplied by x square plus y square over 2q. If you rationalize this complex number and introduce this equation w of z from equation number 13, you can write that the complex number can be written as a magnitude multiplied by the phase factor. So the magnitude is w naught over w. This w is in the denominator is actually w as a function of z from equation number 13, for example, and then we have the phase factor e to the power iota tan inverse of lambda z over pi w naught square, and then of course the other phase factor we have e to the power minus iota k into x square plus y square over 2q. Now substituting q from equation number 4, the field in equation number 15 takes the following form. So let me show you the expression q from equation number 4. This is the expression q from equation number 4. So we get the value of q from equation number 4, and inserting in the equation over here, for example in equation number 15, we get the result as shown in equation number 16. So this is the full form of the field at the output plane. So u as at xyz is equal to w naught over w multiplied by e to the power iota tan inverse of lambda z over pi w naught square multiplied by e to the power minus x square plus y square over w square, which is the Gaussian shape function, and then we have another phase factor e to the power minus iota k x square plus y square over 2r. Now we have to explain these two of them are the phase factors, and because they are having iota with them, and the third one is actually a function. For example, this one is a function that represents the Gaussian wave or Gaussian profile. So let us introduce the parameter zr, defined by zr is equal to pi w naught square over lambda. This zr is known as the Rayleigh range. It is the distance from the beam waist at which the beam spot increases by a factor of square root of 2, that is w of zr, that is the beam, that is the diameter of the beam, that is the radius of the beam at a distance zr is equal to square of root 2 multiplied by w naught. And w naught, you know, that is the diameter of the is the radius of the beam at the beam waist position. You know that beam waist position is the position where the curvature of the wavefront is plane, because we have set there the value of r goes to infinity, because when r is infinity then you have this curvature over there. So you define the beam waist there with a radius of w naught. So Rayleigh range is the distance at which the spot size increases by a factor of square root of 2, as given in equation number 17. So equation number 13 and 14 can be expressed in terms of the Rayleigh distance zr. So we have w square of z is equal to w naught square, and within the square bracket we have 1 plus the square of z over zr. Equation number 18 follows directly from equation number 13, and then from equation number 14 we obtain equation number 19, which is r of z is equal to z into square bracket containing 1 plus square of zr over z. So we have represent previous two equations in terms of z over zr, that is in terms of the Rayleigh range distance zr. The Paraxial Gaussian wave in free space then reduces to, so we can introduce these values wherever possible, and then we can write the field at the xy point, xyz point, which is given over here. So u at xyz is equal to w naught over w e to the power minus x square plus y square over w square, then e to the power minus iota k x square plus y square over 2r, then e to the power iota tan inverse of z over zr. So you see that here we can introduce zr over here. In the rest of the two equations, we couldn't introduce w of z and r of z. But you see that this r in the denominator of equation number 20 with the second phase factor, this r is actually r of z. So we have now introduced r of z over here, and you see that this w is actually, in the first way, this w is actually w of z, and here this is w naught. This w in the denominator is actually w of z. So equation number now 20 gives you the full form of the field at the xyz plane, at the xyz point, in terms of the beam, in terms of the spot, in terms of the laser spot, in terms of the radius of curvature, and in terms of the Rayleigh distance or Rayleigh range or Rayleigh distance zr. Now let's look at the individual functions. For example, the term w naught over w e to the power minus x square plus y square over w square can be identified as the wave amplitude, because it is independent of the complex quantity. So this can be regarded as the wave amplitude. The other factor e to the power minus iota k into x square plus y square over 2 capital R can be considered is actually the transverse phase factor. Transverse phase factor means that this is the phase factor that is contributing at an xy plane. You see that it is independent of the value of z. So this phase factor actually only depends upon the value of xy, because this is the phase vector transverse. Phase factor means that it is transverse to the z axis and it is along the xy plane. And e to the power iota tan inverse z over zr is the longitudinal phase factor, because it changes with the value of z. So that's why it is recorded as the longitudinal phase factor. The amplitude term indicates that the amplitude during the wave propagation remains Gaussian. So look at the shape of this amplitude phase factor, W naught over W, shown in red color. You see that this is the Gaussian phase factor independent of the value of z. So it means that the amplitude term indicates that the amplitude during the wave propagation remains Gaussian, but the spot size changes according to W of z. You see that this phase term contains W in the denominator, W naught over W. So this W in the denominator is as a function of W of z. So this will change with the value of z, or this will change along, that is the spot size will change along the direction of propagation of the wave. In equation number 18, that is in this equation, W of z can be viewed as consisting of two terms, that is W naught square and this factor W naught square into square of z over zr. So if you multiply this W naught square inside, you can consider that this W square of z can be the sum of two terms. One is W naught square, the other term is W naught square multiplied by square of z over zr. So this W naught square into square of z over zr can be broken as W naught square into the square of lambda over pi W naught square, and z square outside that one. So we can combine all these terms together and we can write that this term is actually lambda z over pi W naught whole square, as shown in equation number 21, which arises because of the diffraction, because it contains a term, this term contains lambda, it is lambda dependent. So it means that this term could expand with the variation in wavelength of light, because the wavelength will undergo diffraction. So this term may be due to the factor that the diffraction takes place, and that is why this term is there, because the diameter of the laser beam expands due to diffraction at the aperture from which it comes out. Now using z is equal to zr we obtain. So if you substitute the value over here, that is if you set this value z in the numerator to be equal to zr, what shall we get? We shall get W square of z is equal to 2 W naught square, or simply W of z is equal to square root of 2 into W naught. So you see that at a relay range distance, the spot size would be equal to the square root of 2 times the size at the beam waist, because W naught is the radius at the beam waist of the laser spot, and W of z is the beam spot at a distance z. And here we have taken z is equal to zr, that is the relay range distance. So the spot size at the relay range distance will be equal to the square root of 2 times W naught, as shown in equation number 22. Now let's assume that z is much greater than zr. So here if you consider that z is much greater than zr, then this term in the parenthesis will be much greater than the value of 1. So 1 can be ignored, and we can simply write this term that W square of z is approximately equal to W naught square multiplied by square of z over zr. This is what we have written, that W of z is equal to W naught into z over zr. And this is equal to, if you substitute the value of zr over here, that becomes equal to lambda z over pi W naught. So if you are measuring the diameter, or if you are measuring the spot size at a large value of z, that is z is much greater than zr, then of course the spot size W of z is given by lambda z over pi W naught, that is at large distance w of z varies linearly with z. So if z increases, then of course w of z will also increase, because this is a linear relationship between the spot size and the distance of propagation z. The quantity w of z divided by z can be identified as the beam divergence theta d. So if you draw a diagram where w of z is actually the radius of the beam and z is the distance from the reference point, then you can see that this can be approximated as a tan of theta d. And tan of theta d can be approximated as theta d because this quantity z is very large, so this angle is very small. So this can be represented as beam divergence. And this beam divergence, which is due to diffraction, is given by the relationship shown in 23, that is theta d is equal to w of z over z is equal to lambda over pi w naught. And you see that this beam divergence is independent of the value of z. It only depends upon the value of wavelength of light and the initial spot size measured at the beam waist. Theta d is known as the half divergence angle, because we have measured it only along the half radius, because theta w of z is actually the radius, not the diameter. So we are taking the right angle triangle, in which we are one side, which is the perpendicular side of the right angle triangle, is w of z, and the base of that triangle is z. So tan of theta d, which is nearly equal to theta d, can be given by w of z over z. Since we are measuring in the triangle, so we can regard this theta d as the half divergence angle. The factor w naught over w in the amplitude term will ensure that the total power in the beam spot at any distance z remains the same, provided the medium is lossless. So this will ensure, because you see that we are normalizing it w naught by the factor w. So the factor w naught over w in the amplitude term, and let me show you this amplitude term over here, w naught over w multiplied by e to the power minus x square plus y square w square. So this term you see that is being multiplied over here. So w of z, you know, that is the function of z, which will increase. Then of course this Gaussian profile, you see that is modified, but the shape will remain Gaussian, but of course the width of the Gaussian will expand with w of z as a function of z. When the z will increase, the Gaussian profile will expand, and you see that w naught over w will take care of the factor that the power in that profile would remain the same. So the total power in the beam spot at a distance z remains the same, provided the medium is lossless. So we have explained one factor over here, that is w naught of w e to the power minus x square plus y square over w square, which we have regarded as the wave amplitude. Okay, the plot of the normalized radius of curvature r of z divided by zr versus the normalized distance z over zr for a two-dimensional transverse phase factor is shown in figure 2 for z greater than 0 as well as for z less than 0. So you see that we have r of z, for example, over here in equation number 19. So if we divide this r of z by zr on both sides, and then we have z of r divided by zr from both sides, then we can plot this r of z divided by zr versus z over zr. For both values, for both positive value of z, that is z greater than 0, and for negative value of z, that is z less than 0. And you see that plotting that one, the plot will give you the dots, the dotted curve, that is the curvature of the spherical waves. So these dotted are actually the spherical waves, that is the curvature of the, that is the radius of curvature of the beam is denoted by these dotted lines, and these dotted lines are actually the plot of R of Z divided by ZR versus Z over ZR. And you see that we have shown the beam waist over here. At Z is equal to 0, we have the beam waist W naught as the radius of the beam spot at the location Z is equal to 0. And this, you know, that W naught was obtained when we set when we wanted to have a plane wave at this at Z is equal to 0, and for the plane wave we have set R goes to infinity in one of our equation, probably equation number 4, and then we obtained this relationship. So this dotted line at Z is equal to 0, as at Z is equal to 0 actually represents a plane wavefront. You know that when this plane wavefront will travel either to the left side or to the right side, it will become spherical, and the plane wave has the largest curvature at Z is equal to ZR. That is why the distance Z is equal to ZR, that is the Rayleigh range distance, is also important. You see that here the curvature is maximum, and after that the curvature will decrease. So for the as the curvature will travel, as the radius of curvature of the beam will travel around the Z direction, then the diameter of the radius of curvature will increase. It means that the wavefront becomes smoother and smoother. So this is the diagram. Now you see that what are these solid lines. I have explained the dotted lines. The dotted lines are actually the plot of R of Z, that is the radius of curvature, that is the normalized radius of curvature versus the distance. What are these solid lines? These two black solid lines. One is above the z-axis, the other is below the z-axis. Let me read the caption first. The caption is TEM0000 Gaussian mode. Beam profile in continuous curves. That is this continuous curve, that is the curve in black, which is a continuous curve. Actually this is the beam profile in the continuous curve. Equiphase surfaces in the dash curves. So dash curves represent the equiphase surfaces. Indication of a beam waist at Z is equal to 0. At Z is equal to 0 gives you the beam waist. And the Rayleigh distances, which is Z is equal to ZR and Z is equal to minus ZR, have also been shown. R is minimum at Z is equal to ZR. So the radius of curvature, you know, that is the shortest at these points, and the radius of curvature at the wavefront corresponding to the distance Z is equal to ZR is the minimum value of the radius of curvature, and after that the radius of curvature will increase for the other dotted lines shown, because they will expand, and of course the radius of curvature will also increase. So these solid lines, you know, that are actually the beam profile, and this beam profile is actually represented by this term, which is the Gaussian term, e to the power minus x square plus y square over w square. And in this figure we have either plotted x square over w square or y square over w square. That is one of the variable is what we have plotted, because we cannot plot the two-dimensional variables in a one-dimensional figure. So this is our one-dimensional figure. So either this represents a plot of x square over w square or y square over w square, as shown in over this vector. So we have shown only one of the variables over here, either x square over w square or y square over w square, because both x and y are perpendicular to z direction. So either you plot x square over w square or y square over w square, the figure will be identical. And you know that the radius of the beam at a distance equal to the Rayleigh distance from the beam waist will increase by a square root of 2, which is also indicated in the figure. So the square root of 2 multiplied by W naught at both values of the Rayleigh range distances. The spot size will increase by a square root of 2. And you see that I have also explained the solid lines, and I have also explained these dotted lines, that is the curve. for a one dimension. You see that I have written for a one dimensional transverse phase factor. This factor is actually quadratic, you know that, and we have only one dimension. We have to plot only one dimensional phase, one dimensional factor over here, either x square over w square or y square over w square. That's why we have a one dimensional function picture over here. Okay. And you know that you have this parabola which is extending. If you extend backward this solid line backward, it will meet the z is equal to 0 plane somewhere, and then that distance, then that angle will be the theta d angle, where theta d, you see, that gives you the divergence of the beam. So after a distance beyond z is equal to zr, if you trace back this curve in dotted line to be meeting at the z is equal to 0 plane, then you see that the angle made by the dotted lines, which is not shown in the figure but of course can be obtained by extending the curve, solid curve backward, will give you the angle, will give you the theta d value. That will, theta d value will be the beam divergence angle. The longitudinal phase factor changes sign from minus pi by 2 to plus pi by 2. Where is the, what is the longitudinal phase factor? This is the longitudinal phase factor, z over zr. You see that this is the factor that we have already plotted and we have discussed that one. That is the lines which are dotted in, which are the dotted lines over here. And this phase factor, e to the power iota tan inverse of z over zr, if z extends much greater than zr or much smaller than zr, then of course you see that this becomes nearly 0 and tan inverse of 0 will be equal to pi by 2. Tan inverse of 90 degrees actually pi by 2. Tan inverse of infinity actually pi by 2, because zr becomes so small over here. For example, over here the longitudinal phase factor changes the sign from minus pi by 2 to plus pi by 2 in going from z much less than minus zr to z much greater than zr. So under this condition, you see that z over zr becomes much greater than 0, and w naught at w naught at z is equal to 0 gives you the minimum spot size and is also known as the beam waste. You see that in this figure w naught is the spot size at the equation z is equal to 0, which we call it as a beam waste, and the phase factor due to this term, for example the phase factor which I have shown over here, for example this e to the power iota tan inverse z over zr. So we are considering z is much greater than zr, so this becomes nearly, you see that, infinity. So it will give you tan inverse of infinity will give you actually pi by 2. So this will change its sign from minus pi by 2 to plus pi by 2 when traveling from large values of z much smaller than zr to a very large value of z much greater than zr. The equiphase surfaces with z greater than 0, for example these one, equiphase surfaces on the right hand side of z is equal to 0, have center of curvatures on the left to the surfaces, and thus we have to take r greater than 0, whereas the equiphase surfaces with z less than 0 have centers of curvature on the right side of the surfaces, and thus r is less, will be taken as negative. So these are the sign conventions for the radio of curvature. But here we are not going to use this sign of convention over here, but just mentioned for completeness. Now a few words on the higher order modes of the propagating field. So far we have discussed the field at the output plane, that is u as a function of x, y, z, of a general optical system shown in figure number 2 of the appendix. In terms of the field at the input plane u of x1, y1, z1. That is the field at the input plane x1, y1 and z1 was known, and we have computed the field u as a function of x, y, z. which is also reproduced here through the integral, that is u of x y z is equal to iota over b times lambda double integral over the surface element s, and then we have the field at the input plane, which is u of x1 y1 z1, and then we have e to the power minus iota k multiplied by this phase term, that is a into x1 square plus y1 square plus d into x square plus y square minus 2x1 into x minus 2y1 into y divided by 2 times capital B, and the integration is with respect to dx1 and dy1. This was transformed to the case of a free space propagation using, so you can transform this integral for the case of free space propagation if you set a is equal to 1, capital D is equal to 1, capital B is equal to L, where L is the separation between the two planes as in the figure shown in the appendix, and the integral was solved using an input field of the Gaussian form with the complex radius of curvature q1 as given. So you see that we have initially we have taken that that our initial field looks like this one, and you see that we have also proved that this is nothing but a spherical wave. So u incident field on the input plane u of x1 y1 z1 was proportional to e to the power minus iota k, and then we have x1 square plus y1 square divided by 2q1, where q1 is actually the complex radius at the plane where we have the coordinates x1 and y1, that is at z is equal to z1 plane. Whereas the output field was found to be u of x y z is equal to 1 over a plus b over q1 into e to the power minus iota k x square plus y square over 2q. You can notice that the difference in the phase term is that you have 2q1 because q1 is the complex radius at the input plane and here q is the complex radius at the output plane. These two complex radii of curvature are related through the relationship, that is q is equal to a into q1 plus b divided by c into q1 plus d. This output field represents one of the many possible solutions of the integral in equation number 24. That is, in this equation many solutions are possible due to this relationship. So if many a, b, c, d are possible, then of course many relationships could be possible. A large set of output solutions can be obtained by writing the input function as a product of Hermite and Gaussian functions as given. So you see that a large set of output solutions can be obtained by writing the input functions as a product of Hermite and Gaussian functions, which is shown in equation number 25. So for all the possible set of a large number of set of output solutions, we need to write our input in the following form. That is u of xy, x1, y1, z1 is equal to hl of square root of 2 multiplied by x1 divided by w1. Then multiplied by the Hermite function hm as a function of square root of 2 multiplied by y1 over w1 multiplied by the same phase factor e to the power minus iota k. Then we have x1 square plus y1 square over 2q1, where hl, hm are the Hermite polynomials of order L and m. w1 is the spot size at the input plane location, which is over location z is equal to z1. The corresponding field at the output plane, which is at z is equal to z2, is obtained by solving the integral. So we shall get the output as shown in equation number 26. In terms of the when we have used this as the input in the integral, so we have the output function, this one, that is u, output field u as a function of x y z is equal to 1 over a plus b over q1 raised to power 1 plus l plus m multiplied by hl as a function hl, Hermite polynomial hl, as with an argument of square root of 2 multiplied by x over w, and then hm multiply as a function with an argument of square root of 2 multiplied by y over w, and then the phase factor e to the power minus iota k, and then we have x square plus y square over 2q as shown in equation number 26, where w is the spot size at the output plane, and 1 over q is equal to 1 over r minus iota times lambda over pi w square. See equation number 4 for this one, from where the value of q1 is obtained. by assuming that the beam waist exists at the input plane z is equal to z1 where r goes to infinity. So if you want that the input plane should be a plane wavefront, you need to set r goes to infinity there at the z is equal to z location, and then you see that your 1 over q1 will be equal to minus iota times lambda over pi w naught square, and you see that then you will have substituting a q and q1 into equation number 26. So we obtained the following relationship. So you see that in equation number 26 we have q1 over here and we have also q present over there. So using the value of q and q1, we have obtained the value of q1 assuming that our input plane is located where the wavefront is a plane wave, because we have set the value of r goes to infinity in equation number 4. So if you set r goes to infinity in equation number 4, you will get 1 over q1 is equal to minus iota times lambda over pi w naught square. So using the q1 from here and q from this equation, we can obtain the following relationship. That is the full form of the field independent of the dependence on the value of q1 and q. We obtain u as a function of x y z is equal to w naught over w multiplied by hl within some argument, hm with some argument, and then e to the power minus x square plus y square of w square, which is a Gaussian profile, and then we have e to the power minus iota k, then x square plus y square 2 capital R, and then e to the power iota contains 1 plus L plus m, and this whole parenthesis is multiplied by phi, where w is actually w of z and r is actually r of z, have been defined in equation number 13 and 14 respectively, and phi is equal to tan inverse of z over zr. M is equal to 0, M is equal to 0 gives the field corresponding to the lowest order mode known as the TEM00 mode, which we call a transverse electric magnetic mode, or the Gaussian mode, also known as the Gaussian mode. TEM00 mode is known as the Gaussian mode and is given by, so setting so using L is equal to 0 and M is equal to 0 in equation number 27, we get u of 0 0 as a function of x y z is equal to w naught over w e to the power minus x square plus y square over w square, then e to the power minus iota k over x square plus y square over 2r, then e to the power iota tan inverse of z over zr, where we have h naught and h naught both due to L is equal to 0 and M is equal to 0 are equal to 1. For any distance z, the intensity of TEM00 mode is always Gaussian on the transverse xy plane as shown in figure number 3. For example, this one, this is TEM00 mode. You can see this is the spot of the laser beam. Some higher order modes are also shown in the figure. For example, I have also shown TEM01 mode and TEM11 mode. The subscripts LM give the number of zeros along the two transverse directions within the beam spot. So you see that these are the spots which are perpendicular to the z direction. While looking at this figure, you can see that the z axis is pointing towards the reader. So and the xy plane, this figure is in the xy plane, whereas the z axis is pointing towards u, that is pointing towards the reader. So this is the TEM00, that is the Gaussian mode, and the next one is the TEM01 mode. 01 mode, if you move from left to right, there is no 0, so that's why we have 0 over here, and in the subscript you have 1. So if you move from bottom to the top, you will see that there is 1 0 between the two lobes. And in this figure, on the right hand side, you will see that it is a TM11 mode. So if you travel from left to right, you will encounter 1 0 in the middle, 1 0 in the middle, and if you travel from the bottom to the top, you will encounter another 0 in the center. So that's why it is a TM11 beam. Shape of the beam spots in 3 modes that is TEM00 mode, TEM01 mode, and TEM1 mode, 11 mode. So you see that I have explained in much greater detail the Gaussian profile, TEM00 profile. I have discussed the beam waist. I have discussed the Rayleigh distances. I have discussed the profile of the beam as Gaussian, discussed its beam waist, discussed the how we can find out the radii of curvature, that is the value of r, that is r as a function of z, and similarly w as a function of z. These expressions have been derived. I have also calculated the field u as a function of x, y, z at the output plane using a general optical system shown in the appendix. And then we have also because when the field when the input field has a form as given in equation number 25, and I have also expressed them in terms of the ABCD matrix, and also the integral has also been given in terms of the ABCD matrix, which gives the relationship between the output field and the input field in terms of the ABCD variables. And of course the basic mode TEM00 mode along with the higher order modes have also been briefly discussed. And you see that this was the appendix in which we used this as our general optical system, in which the field has also been shown on the two dotted planes. One is located at z is equal to z1, the other at z is equal to z. And this is the equation that has also been mentioned while I was delivering this lecture. So you see that this is the end of slide number 81.